Today we're going to continue looking at quadratic functions. Let's review the things that we've looked at so far. We have two forms of quadratic function. We got the standard form ax squared plus bx plus c, and we have the vertex form a times the square of difference between x and h plus k. We know that the leading coefficient, will determine whether the parabola opens up or the parabola opens down. And we know how to find the vertex, whether we are given a function in standard form or function in vertex form. In vertex form, the vertex is just going to be at hk. That's why we call it the vertex form, because it has the vertex right in the form. And for standard form, we can calculate h as minus b over 2a. Right now, that's just a formula taken out of context and just telling you that that's how you can find it. But we can see where that comes from today when we start getting into the manipulation of the equations. Once we have the x-coordinate of the vertex with negative b over 2a, we can just plug that into the function and figure out the y-coordinate of the vertex. Another important thing that we know about quadratic functions and parabolas is that they are symmetric about a vertical line through the vertex called the axis of symmetry. What that means is that points that are the same horizontal distance from the axis of symmetry have the same y-coordinate. So if the vertex is at h and k, and we have 2 points with the same y-coordinate, they will be the same horizontal distance from the axis of symmetry. What this means in the numbers is that if we're looking at a table of values, in the middle we'll have the vertex h and k, and if we have the same y-coordinate, if we have, say, 10 on one side and 10 on the other side, then these points are going to be the same horizontal distance from the axis of symmetry. So here we have the same y-coordinate of 10. They'll be evenly spaced about the axis of symmetry. So they'll be, if this one is 3 units away, then the other one will be 3 units away in the other direction. I should have picked a value for h, but we don't have that, so I'll just have to say h plus 3, and on the other side is an h minus 3. The important thing to recognize is that it's the vertex, the x-coordinate of the vertex in the middle, because that's the axis of symmetry. So here are 2 points that are the same distance away from the axis of symmetry at h, and we end up with the same y-coordinates. So that's the symmetry visually, and this is how we see that symmetry when we look at numbers. This plus and minus business is important when we start trying to solve equations. So when we want to solve a quadratic equation, one of the things that we'll want to know is where the middle is. Because when we're solving a quadratic equation, we're looking for the x-intercepts of the graph. So today we want to talk about solving quadratic equations. So today we want to talk about solving quadratic equations, and we want to use what we know about parabolas to do it. We want to tie this very closely to the graph so that we can understand this concept in many different ways. So what we want to know is that when we're solving a quadratic equation, we are looking for the x-intercepts of a quadratic function. So I'll write parabola. Find the x-intercepts of some parabola, because a parabola is the graph of a quadratic function. And we're also, from an equations standpoint, trying to solve an equation of the form f of x equals 0. So ax squared plus bx plus c equals 0, or a times x minus h squared plus k equals 0. So solutions to equations, x-intercepts of a parabola, and there'll be zeros of a quadratic function. So we'll refer to the zeros when we're talking about the function. We're referring to solutions of an equation, and we'll refer to x-intercepts of the graph. X-intercepts of the graph, solutions to an equation, zeros of a function. A lot of times we will mix these up. A lot of times I'll say find the x-intercepts of some function. It sounds a little weird every time I say that. It'd be like saying I'm piloting my car. You're not piloting your car, you're driving your car, but it's the same kind of thing. You're operating the vehicle. We just have different words for operating different vehicles. Like driving a plane is not how we say that. But if someone says they're driving a plane, we get the idea. So if someone says we want to find the zeros of this parabola, we get what the idea is. All right. The important thing to note about the solutions to the quadratic equation, or the x-intercepts of a parabola, or the zeros of a function, is that the x-intercepts will have the same y-coordinate. And so that means they'll be the same distance away from the axis of symmetry. So x-intercepts have the same y-coordinate, 0. So the x-intercepts will be the same distance horizontally from the axis of symmetry. So the x-intercepts will be the same horizontal distance from the axis of symmetry. This is going to give us a plus or a minus. It's going to be h plus or minus some amount. So the axis of symmetry happens at h. And then we'll have this plus or minus some horizontal distance. For those of you thinking about the quadratic formula, that's the plus or minus. So the quadratic formula has a negative b plus or minus the square root of b squared minus 4ac, and then all that's over 2a. That plus or minus is the horizontal distance. In the middle, we have the axis of symmetry, h, which is negative b over 2a, and then it's plus or minus that horizontal distance, the square root of b squared minus 4ac all over 2a. So rather than just trying to memorize the quadratic formula, let's look at how these two equations are supposed to say the same thing. And let's play with this for a little bit. So let's consider the vertex form. So I have a times x minus h squared plus k. And let's just perform the operations that we see in the vertex form. Let's perform the operations. So I have a times x minus h squared plus k. I can, the order of operations is exponents before multiplication. I guess if you're thinking of PEMDAS, which you shouldn't because PEMDAS is trash, x and h, we can't combine these in any way. This is already taken care of. This is just x minus h. Those aren't like terms. I can't add them. So parentheses is not an operation anyway. So we're going to take the exponent of x minus h. So I have x minus h times another x minus h. That'll give us an x squared minus an hx minus another hx plus h squared. So I have x squared minus 2hx plus h squared. That's just the x minus h squared. So now this is equal to a times x squared minus 2hx plus h squared plus k. Now if I multiply through by a, if I use the distributive property, now that I've done my exponents, I can do my multiplication. We end up with ax squared minus 2ah times x minus ah plus ah squared plus k. So first I did the exponents, and now I'll take care of the multiplication because that's the order that we should do those things. And this is supposed to equal the standard form. Notice I have an x squared term, I have an x term, and I have this constant term. So this should equal the standard form. Ax squared plus bx plus c. Now, if these two things are going to be equal, the x squared terms, notice that those two are the same. Ax squared and ax squared. That's good. Otherwise, things have gone horribly wrong, and we have to fix something. But we also want to look at this minus 2ah times x, and then the x term in the standard form is bx. So that means that minus 2ah has to equal b. And if I solve this for h, I get minus b divided by 2a. Really, I have b divided by negative 2a, but we always write the minus out in front. So here's one way we can justify that the x-coordinate of the vertex is the opposite of b divided by 2a. We also have that ah squared plus k is equal to c. Which is not quite as useful. It involves kind of too much stuff. So it would be easier to find the y-intercept by just plugging in 0. All right, so now this justifies our formula h equals negative b over 2a for the x-coordinate of the vertex. We should be able to get the y-coordinate of the vertex by plugging negative b over 2a into the standard form. Let's try that. Let's say k. We know that k is equal to the function evaluated at h. So let's take let's take f of x and plug in negative b over 2a. So a times negative b over 2a squared plus b times negative b over 2a plus c. This will give us an expression for k in terms of a, b, and c. Just following our order of operations, negative b over 2a all squared, that's going to be a positive b squared over 4a squared that has to get multiplied by a. Plus and minus is going to multiply out to be a minus. And I'm going to multiply b times b is b squared divided by 2a. And then we still have this plus c. Just going to hit this with the algebra stick a little bit. In this first term, I have an a divided by an a squared. I can simplify that. So let's simplify that. So let's cancel an a and a squared, just leave behind an a. So that first term becomes b squared over 4a. And then the second term is minus b squared over 2a. And then we still have this rogue plus c. Now, these two have the same constants, a and b, and the same exponents, but different coefficients. So I have b squared over 4a minus b squared over 2a. I can add these together if I get a common denominator. So I get b squared over 4a. If I multiply the second fraction by 2 over 2, I have b squared over 4a minus, I'm going to multiply by 2. I still have a plus c. Oops, I haven't done anything with that. And so now I'm looking at b squared over 4a minus 2b squared over 4a. So I have one of these b squareds over 4a minus 2b squared over 4a. So I'll have minus a b squared over 4a plus c. Because now I can combine like terms. Oops, now a common denominator. We can also look at this and say if we have 1/4 of something minus a half of that thing, we'll have minus 1/4 of that thing. So that would be an alternate view of what's going on here. We might look at this and say, to help us see things differently, 1/4 of a thing minus 1/2 of that thing is minus 1/4 of that thing. If you have 1/4 and someone takes 25 cents and someone takes away 50 cents, you have negative 25 cents. A quarter minus a half is negative 1/4. So that's another way to arrive at this minus b squared over 4a plus c. So that's k. Now look, if we go back to what we had up here, if we solve for k in terms of from this standard form, we have that k is equal to minus ah squared plus c. And if we put h squared in, or sorry, if we put h in for the h squared, I'll have minus a times h, which is negative b over 2a, squared plus c. And I smeared my other stuff. So if I square the b, I get b squared over 4a squared, and one of the a's will cancel out. And so I end up with the same thing for k. So that's good. It's nice when everything works out. Now, is all this stuff that you have to memorize? No, absolutely not. You do not want to remember that k is negative b squared over 4a plus c. You do want to remember that h is negative b over 2a. We don't want to remember it just because that's the formula, but we want to remember it because if we take the vertex form and multiply it out, we should be looking at the standard form. And then so the coefficient of x on the multiplied out vertex form should be the same as the standard, the coefficient of x in the standard form. We did want to throw a lot of algebra at this problem because this is an algebra class. And so we want to make sure that the algebra all works out. So last thing I want to look at today, page 2, is actually solving a quadratic equation. We want to be able to do this from the vertex form. And then from the standard form. So we want to be able to solve quadratic equations from the vertex form and from the standard form. First, let's look at vertex form, because here we can do inverse operations in reverse order. Here we can perform inverse operations in reverse order. So if we're looking at, say, a times x minus h squared plus k equals 0. If we look at the things that happened to the x, if we think about what turned an x into a 0, the first thing we do in the order of operations would be to subtract h. So that's going to be the last thing that we undo. After we subtract h, we raise to the second power. That's going to, in the inverse, make a square root, which is where the plus and minus is going to show up. And then third, we multiply by a. And fourth, we add k. So there's our plan. If we take the inverse operations in reverse order, that will give us a plan to turn the 0 back into an x. So first, we're going to subtract k. Second, we'll divide by a. Third, we'll do a 1/2 power. We'll do a plus or minus square root. And fourth, we will add h. So our solutions are x will be, we'll start off with minus k. 0 minus k is minus k. Then we'll divide by a, so minus k divided by a. And then we'll do a square root, a plus or minus square root. So I have plus or minus the square root of k over a. And then finally, we'll add h. So I have h plus or minus the square root of k. Oops, forgot the minus. Our solutions will be h plus or minus the square root of minus k over a. This is not the quadratic formula. This is not even a formula that we should just remember. This is a process that we can use to solve the equations. We want this to be going on in our minds so we don't have to write all this stuff down. The point of being in a math class is to get to the point, practice things enough that you don't have to do all the writing down anymore. So if I have an equation that says 5 times x minus 3 squared, let's go with minus 7 equals 0. Our solutions, first we're going to add 7, then divide by 5, then we're going to do a plus or minus square roots, and then we're going to add 3. So we can go right to the answers. The whole point is not writing all this stuff down in the middle. We'll add 7, divide by 5, then we'll undo the square root, so we'll have a square root, but we're solving an equation, so we need a plus and a minus, and then we'll add 3. If we need approximations of these values, we can just grab a calculating machine. And I can go 3 plus the square root of 7 over 5. So our approximations will be 4.183. And I'll do the same thing, but with minus the square root of 7 over 5. 1.817. Notice that in the middle is a 3, and then we add and subtract the square root of 7 over 5. So if I look at the square root of 7 over 5, that's 1.183. So I take 3, add 1.183, and 3 minus 1.183. There's the plus or minus. The square root of 7 over 5 is 1.183. So the 4.183 is 3 plus 1.183. And the 1.187 is 3 minus 1.183. We knew that that 3 was going to be in the middle because there it is in the vertex. We can see the vertex of this parabola. Is at 3, -7. Points with the same y-coordinate, 0, will be the same distance away from the vertex, same horizontal distance away from the vertex. And that horizontal distance is minus k over a, the square root of minus k over a. So that square root of k over a is the same, that's the same horizontal distance that we were referring to before. The same horizontal distance from the axis of symmetry. H is where the axis of symmetry is. So we start off with H in the middle, and then we add and subtract that horizontal distance. So if we're looking at a function in an equation in standard form, this must have a vertex form out there. So the main way I want to go after solving an equation in standard form is by invoking the quadratic formula, which I think is trash, but is something that we're usually inflicted with. So if we recall the quadratic formula, we know that the solution, this is something that we've probably been forced to memorize. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Moving forward, this is something that we should know this. If you sing it to the tune of Pop Goes the Weasel, then you'll never forget it. So it works. That's why I still want to leverage this, but it hides a bunch of stuff that we might care about. That being the symmetry in the parabola. But if we look at this negative b plus or minus the square root thing over all divided by 2a, what's happened here is we've taken a fraction and found a common denominator and just combined everything over one fraction, ignoring all the cool symmetry that we have. If we rewrite this, if we use the distributive property, I can separate out minus b over 2a. There's the middle. There's the axis of symmetry. And then there's this plus or minus the square root of b squared minus 4ac all over 2a. So if we just use the distributive property, we can separate out these two terms. Now that 2a has been simplified. That's where the common denominator came from. But if I think of the 2a as the square root of 4a squared, I can write this expression as, let's see, we have this negative b over 2a still indicating the middle, plus or minus the same horizontal distance, which is going to be one big square root of b squared minus 4ac all over 4a squared. Now, if we continue to think in terms of algebra, and we go back to what k is equal to. K is equal to this minus a times the where'd it go? That was not the one I was looking for. Minus b squared over 4a plus c. And our same horizontal distance should be plus or minus k over a. So here's the square root of minus k over a. So this part right here, this plus or minus square root, the b squared minus 4ac over 4a squared is equal to the minus k over a. So this part must be, this b squared minus 4ac over 4a squared must be a minus k over a. So let's rewrite it. Let's do some more algebra. Let's see, there's a k, if there's a minus and a 1 over a, that's going to leave behind a minus is going to change the order. 4ac minus b squared over 4. I forgot where I was going with this. So the important thing is the b squared minus 4ac all over 4a squared, or this b squared minus 4ac over 2a. This is going to be that same horizontal distance. This is where we have had in this problem, the vertex problem, a square root of 7/5, the 1.183. So the quadratic formula is usually phrased in terms of all over 2a, but if we separate it out, we can see what the middle is going to be. So on Monday, what we want to do is think about how we can leverage this to go from ax squared plus bx plus c and turn that into a times x minus h squared plus k. How can we leverage this information to turn a standard form into a vertex form? All right, that's going to do it for today. That's going to do it for this week. Everybody have a nice weekend, and I will see you all next time. Thanks for playing.